So yeah, we'll start. Let the others join in the meantime. So I would like to introduce myself. This is Ayankara Karthika. So I am a research scholar from IIT Hyderabad. So I'll be handling the problem solving sessions for the NPTEL course, that is Computational Fluid Dynamics. So I hope you all saw the announcements in the course portal itself. So we will be having 12 sessions. In each of the session, we will be solving problems related to that week. So I would like the session to be interactive. So if you have any doubts in between, you can ask. And also if you have answers, you can always unmute yourself and answer. Uh, so if you want to say something, you can say now. Okay. So computational fluid dynamics, it is being used everywhere almost. For all the applications we can use the CFD techniques. So it will minimize the experimental cost whenever we are dealing with experiments, because we can't do experiments at such large scale. So that is one of the things. And also we can do design analysis of the system. So all these things is made feasible through CFD. So that is the main motto behind why we are dealing with CFD techniques, because we can't always perform experiments to study that particular system. And if you want to design any new system, like we can use the CFD technique to analyze the system once we know the uh, pre uh, uh, beforehand the previous data. For example, if we know CFD, I mean if we experimentally we know how a fluidized bed reactor or any other thing behaves, we can simulate a model to capture that using CFD, and later on with the same parameters and same models, we can scale up or scale down or see any other things in CFD. So that is just to give you an idea. So the normally if we say CFD, what comes is like we have lot of calculations and lot of equations to be solved, and we at the end after solving those we'll get a vector plots or whatever our requirement is. So the results should be accurate enough when we are dealing with when we are using CFD techniques. So it should be like proper things to be handled. For example, when we are using equations, I mean we generally mesh the system and solve equations for each particular grid. There are several techniques. So the after by the end of this course, you'll be able to say like this equations, this method works well. So that is the thing what you will be gaining, because it is a vast area. CFD is like it has a vast, it has various scopes. Also like studying that involves various like concepts. So I hope that would help. And we'll start now. So yeah, as I mentioned, this is the computational fluid dynamics and the course code is NOC 25CH18. And this is our first session. Actually, two sessions are being held. One is conducted by myself. On every Saturday, you will be having these sessions. That is Saturday 3 p.m. to 5 p.m. We'll have the sessions. Like for 12 weeks, we'll have. And one more session is handled by another TA on, I guess it is on Monday. So if you are interested, you can check that out as well. But concepts will be same. Depending on your convenience, you can join any of that. So, as you all know, the course instructor is Professor Sreenivas Jayanti from IIT Madras. So, his course lecture notes and lecture videos, I hope you have seen by now. The first week content was available, and also the content for the second week is made available from yesterday. So, he will give, I mean, his lectures will be posted. The concepts, everything will be from that only. These sessions are just to summarize what happened in that, and also like solving assignment problems so that it will be helpful for you when you are dealing with assignment submissions. So I hope you remember that every week you have assignments to submit. It adds a certain percentage of your marks in the final exam. So submit your assignments on time as well. So these problem solving sessions are a way to help you guys in solving the problems for the assignments. So yeah, that myself the TA from I'm a research scholar from IIT Hyderabad. So we'll see now. So as we were saying, it is an NPTEL course and it is a 12 weeks course. So what are we seeing is that a course layout just to give you an idea. So in the first week, it is about introduction and calculation of flow in a rectangular duct. And second week, it will be fully developed flow calculation in a triangular duct. And third week, it is derivation of equations governing fluid flow. And fourth week, it is equations for incompressible flow and boundary conditions. And fifth, it is basic concepts of CFD, finite difference approximations. And sixth, it is concepts of CFD, consistency, stability, convergence. And it is solution of Navier-Stokes equations for compressible flows. And later on, we are moving to incompressible flows. And solution of linear algebraic equations, basic methods. And finally, we would be like seeing advanced methods and finite volume method, including grid generation. So mostly here we are dealing with finite difference method, and later on it is finite volume method, and lastly it is turbulence flows and turbulence modeling. So basically what CFD is, we'll see after 2 slides. So in the first week, I hope you have seen the lecture videos. In that, it would be like about given in introduction and also about the calculation of flow in a rectangular duct. So when fluid flows in a rectangular duct, how it is, how the calculations are made. And as per the books and references, actually these week course layout and books and references I have taken from the NPTEL website only, so you can check that out as there as well. And also the lecture videos, I mean not lecture videos, the problem solving session videos and this particular PPTs will be updated, uploaded as well, and you will be given the links for the same, so you can use that for your future references if required. So coming back to books and references, the first one is Computational Methods for Fluid Dynamics by Ferziger and Perick. And second is Hirsch, Numerical Computational of Internal and External Flows. And third one, it is Patankar, Numerical Heat Transfer and Fluid Flow. And fourth, Westig and Malalasekara, an Introduction to CFD, the Finite Volume Method. And last, it is Anderson, CFD, Basics with Applications. So I have used this book, CFD Basics with Applications. So if you are a beginner and want to get hands-on on CFD, you can just read this because it will give you an idea of what CFD is and how we will be proceeding. So coming to the CFD concept, so I hope in the lecture it was introduced, you people were introduced to CFD techniques, and also what about what is how we were solving the equations for flow in a rectangular duct. So all these things are said, what is CFD? So in general, like experimental fluid dynamics, we like in terms of fluid dynamics experiments, it all started in 17th century. So later on, like to visual apart from the experimental techniques, in order to understand more and have and get in-depth knowledge of the domain, theoretical fluid dynamics were developed in the 18th and 19th centuries. So we have experimental knowledge and also we have theoretical knowledge, but something was like still needed to be done. So there came the computational fluid dynamics. Why was it needed? Because like experimental techniques is like costly, like you can't always perform the experiments. And coming to theoretical fluid dynamics, every time you can't get the solution analytically, and you need to find some other way to get the solution. So there came the computational fluid dynamics. So computational fluid dynamics, it each of them complements each other. Like computational fluid dynamics alone single-handedly can't give or cannot prove anything. Like it requires some knowledge also from the other aspects, theoretical fluid dynamics, experimental fluid dynamics, everything. uh, Okay, if there is anything, just let me know by unmuting yourself, because it is difficult for me if to see if any messages are being posted. So if you have any concern, please unmute yourself and speak. While otherwise, it is bit. I might not see the message during the time. I might see only during the break. So I apologize for that. So if you have any concerns, please unmute yourself and you can say. So coming back, so CFD, it complements each other. It single-handedly it cannot do anything. Similar way, experimental knowledge alone for a small scale system, it cannot be used for a largest wide range of applications. So each of them is required for different applications. So that is how the system works. So as I mentioned, like computational fluid dynamics, it basically it is like solving equations. That is what we do in CFD. And for that we require the knowledge of fluid dynamics, and for solving equations we require the knowledge of numerical methods, which I hope most of us have studied. I mean I'm not very sure of in which semester you people are, if you are in BTech or if you are in MTech, and how much knowledge you have. But in general, like I'm assuming like fluid dynamics and numerical methods courses have been over. So in that case, like we require the knowledge of fluid dynamics, and we require the knowledge of mathematics as well. Why do we require? Because we need to know physics behind the system. We always need to know. If given a system suddenly and we are asked to simulate, we do not know what is happening inside the system first of all, and thereby we cannot give exact conditions for it to be simulated. So we need to know the actual physics behind the system, and also we need to know certain mathematical concepts for us to simplify the equations. Like for example, to give you a basic idea, what we do in CFD is we solve the conservation of mass and conservation of momentum equations. That is mass conservation equations and momentum conservation equations, so that we know how a momentum is exchanged and how mass is conserved inside the system. These two equations are simply solved when we are dealing with, I am talking about the systems where only fluid is present and it is a cold flow system. There is no external heat transfer taking place. In those cases I am talking about, if heat transfer also comes into picture, we have additional equations like energy equations as well. So, and if particles comes or multi phases come, it becomes a different story. As far for a single fluid flowing inside a system, we are talking about two equations, that is mass conservation equations, that is continuity equation, and momentum conservation equation, Navier-Stokes equations. So all these are partial differential equations. So we need to, in order to convert them, I mean solve those equations, we generally use some concepts and get it in the algebraic equation form and solve that. So we need to have the mathematical idea as well. And all these equations, even after obtaining that, it is not feasible to solve it by hand. So we need to know, use the computational power as well. Only then we can successfully get the solution within a time. Like if the simulation, or if the system is taking a lot of time to simulate that particular, it would not be very useful. So all these things have a part in CFD, that is computational fluid dynamics. So as I was saying, we solve the equations, that is what we are doing. So what exactly happens in CFD? We were all talking about CFD. So what happens in CFD is that we can divide it into three steps actually. That is pre-processing, solving and post-processing. So let us come back to the fluid flow in a single pipe as well. So first it is pre-processing. I am talking about the case when you are using certain CFD tools to get the solution. So in pre-processing, you are about to simulate the fluid flow inside a pipe. So you need to know the pipe geometry and you need to mesh the pipe. Meshing is nothing but you are dividing the pipe region into smaller, finer segments. Why do we divide? Because CFD is nothing but solving the equations. At what points we solve? We solve the equation at all those grid points. So we need to know so many number of points in the like pipe. So for example, if this is your pipe, we are just dividing it into so many divisions. It would be finer divisions. So only then we can use the system to get the, we'll be solving the equations at all these grid points. So for that we are meshing. So that is what happens in pre-processing. Like we are defining the mesh geometry. We are defining the pipe geometry and we are meshing the pipe. That happens in pre-processing. Second one, it is solving. In solving, we solve the equations. For example, mass conservation or momentum conservation equations. We solve and we get the values of, for example, if fluid flow, we might need to know about the velocity of fluid at all the points. So we solve for those. And in post-processing, it is nothing but where we get from the obtained information, we may use it to get different plots and get different observations from that. So these are the three basic things that we do in CFD. That is pre-processing, solving and post-processing. So I hope some basic information you have got from on the introduction to CFD. It might not be clear for now, but as you go through the course, everything will be clear. And if you have time to read, I would suggest you to read Anderson book on CFD to get a basic idea on what CFD is. So let us now move on to problem solving. So for week 1, what we have in our hands is that we have actually some few practice problems and few sample problems. So we'll start with practice problems. And for question 1, if you have any answer, you can unmute yourself and see. So these are like simple questions only. So question 1, it is, which of the following formulae is a good, okay, just a minute. Which of the following formulae is a good approximation for dou square u by dou y square at grid point I comma j? So the question is very simple. So like as I mentioned, we'll be solving equations for continuity equations or momentum conservation equations. Those equations, if you remember, it will be containing partial differential terms, dou u by dou x, and on the right hand, for example, in Navier-Stokes equations, you have dou u by dou x, dou u by dou y, and dou square u by dou x square, dou square u by dou y square, all those things. So I mentioned that we will be discretizing those equations. That is, we will be converting the partial differential equation into algebraic form and get the solution. So how do we get convert it from partial differential equation to algebraic form? We use discrete finite difference method or like any other method to discretize the equation. Like here we know we are using at a point and getting an approximation. So for in this particular question, it is about which of the following formulae is a good approximation for dou square u by dou y square at grid point I comma j. So options we will see first. So option A it is uj minus 1 I comma I minus 2 uj comma I plus uj plus 1 comma I divided by delta y square. Second one it is uij minus 1 minus 2 uij plus ui comma j plus 1 divided by delta x square. And C it is u I comma j minus 2 u I comma j plus 1 plus u I comma j plus 2 divided by delta y square. And D none of the above. So answer is actually none of the above is the right answer. So we'll see that how in the next slide. So first let us first see how we are discretizing the system. So consider this as some system and our concerned point is P, that is I comma j. Which of the following formulae is a good approximation for dou square u by dou y square at grid point I comma j? So this is how we divide the system. Here we are dividing it in equally, like 1 unit from left and 1 unit, I mean 1 unit horizontally and 1 unit vertically. In that manner we are dividing. But all the time the discretization won't be, meshing won't be like this. Sometimes it would be non-uniform also. That all those things you will study later. But for now, this is our point of concern. That is P at I comma j, and I is in x direction and j is in y direction. So I is delta x. Here from one point to other we are having the difference in the distance as delta x, and from one point to other in the vertical direction we are having the distance as delta y. So P at I comma j, and here we have okay, this is therefore I minus 1 comma j, and this is I plus 1 comma j, and from top to bottom we have I remains the same because it is in the same x coordinates, whereas the y coordinates vary. It is top it is j plus 1 and in the bottom it is j minus 1. So we'll see how we are getting the solution for dou square u by dou y square at I comma j. So we have actually two methods for this particular problem. The first one is Taylor series approximation, wherein we get it for this one. So it is here, if we have u value at u at I comma j, we get actually value for u at I comma j plus 1, because we are dealing with y. The question is about dou square u by dou y square. We are actually dealing in the y direction. So we are getting u at I comma j plus 1, that is this point u at I comma j plus 1 is equal to u at I comma j plus dou u by dou y at I comma j into delta y plus dou square u by dou y square at I comma j into delta y square, and so on. We are approximating it till this point only. And the second one we are having u at I comma j minus 1, and this is like forward, this is in the backward. So it is from Taylor series approximation we have u at I comma j minus 1 is equal to u at I comma j minus, here you are able to see that we are having minus in all the odd terms, like next term will be negative and so on. All those things we saw in Taylor series approximation itself. I hope you remember. If not, you can go back and check also. Like u at I comma j minus 1 is equal to u at I comma j minus dou u by dou y at I comma j into delta y plus dou square u by dou y square at I comma j into delta y square. So what is our interest? our interest is dou square u by dou y square at I comma j. So this term should remain. So if we subtract, it will be eliminated. So we are adding up. So adding 1 and 2, we have ui comma j plus 1 plus ui comma j minus 1 equal to ui comma j plus ui comma j. We are getting 2 times of ui comma j plus these two terms get cancelled, and again these two adds up. 2 times of dou square u by dou y square at I comma j into delta y square. Now we are rearranging it and we are getting it as just putting it that side and bringing those terms to this side. We are having 2 times of dou square u by dou y square at I comma j into delta y square plus 2 times of ui comma j equal to ui comma j plus 1 plus ui comma j minus 1. So now we have this term alone here and take the rest of the term to the other side. So it is dou square u by dou y square at I comma j equal to ui comma j plus 1 plus ui comma j minus 1 minus 2 times of ui comma j and whole divided by 2 times of delta y square. So that is how we get the answer. So what the correct expansion for dou square u by dou y square at I comma j is, it is u I comma j plus 1 minus 2 u I comma j plus u I comma j minus 1, here plus 1 and here minus 1 divided by 2 times of delta y square. So if we go back and look at the options given, we'll see how we can eliminate it first. J. Okay, the first option is correct in terms of these coefficients. That is u at I comma j minus 1 minus 2u at I comma j plus u at I comma j plus 1 divided by delta y square. So what mistake is visible here? It should be 2 times of delta y square, but it is missing. The 2 is missing, so it is false. And in the second one, even though it is like 2 times of u I comma j minus 1 minus 2u times of I comma j plus u at I comma j plus 1 divided by delta x square. However, in the question we are dealing with dou square u by dou y square at I comma j. It is dou y square, so B is false. And coming to C, again it is u I comma j minus 2 u I comma j plus 1 plus u I comma j plus 2 divided by delta y square. So two things are missing in this particular option, that is 2 is missing, and also the question is at grid point. Question specifically asked dou square u by dou y square at grid point I comma j. So C is also false. So answer is therefore D. So now going to second method. So I hope why the options were false and answer was none of the above, that is clear. So this is one method of finding the approximation for dou square u by dou y square at I comma j. So now let us check method 2 as well. In method 2, it is that we are using central difference scheme for first order derivative and we are getting the answer. So first one, it is first order derivative. The question, it is asked for second order derivative, but we are using first order derivative. So this is just to give you an idea. You need not do these many things in the solution because that is a straightforward question. You all remember most of the time what is the answer. But just to give you an idea, if anything complex comes, you can apply these techniques. So that is the motive behind giving two methods. For this particular problem, you need not use these two methods as well, methods at all, because most of the time we know the approximation for dou square u by dou y square. This is just to give if any complex equation comes. So second one is central difference scheme. So first one, we are first getting for first order derivative. So it is dou u by dou y at I comma j equal to u at I comma j plus 1 minus u at I comma j minus 1 divided by 2 times of delta y. Now we have dou square u by dou y square at I comma j. This becomes, we are just taking the second derivative for this. That is dou by dou y of dou u by dou y. Dou by dou y of dou u by dou y at I comma j. So this becomes dou by dou y of dou u by dou y. Dou u by dou y is u at I comma j plus 1 minus u at I comma j minus 1 divided by 2 times of delta y. So substituting this, we are having this expansion, and now we are taking dou by dou y at all these points. So dou by dou y of u at I comma j plus 1 minus dou by dou y of u at I comma j minus 1 and divided by 2 times of delta y. And we are having for I comma j minus 1, we are using the forward difference. It is u at I comma j minus u at I comma j minus 1. So I comma j minus 1, so forward difference is I comma j and I comma j minus 1 point divided by delta y. And for when we are using backward difference, dou u by dou y at I comma j plus 1, we are having u at I comma j plus 1 minus u at I comma j divided by delta y. So substituting all these things back in equation 2, substituting 3 and 4 in equation 2, we are having dou square u by dou y square at I comma j is equal to u I comma j plus 1 minus u I comma j divided by delta y minus u I comma j minus u I comma j minus 1 divided by delta y divided by 2 times of delta y. So how this becomes? U I comma j plus 1 minus 2 times of u I comma j plus u I comma j plus 1. I mean j plus 1, j minus 1. 1 is j plus 1, 1 is j minus 1 divided by 2 times of delta y square. So this is the approximation. So in both of them we obtain the same, but it was not there in the this is the actual approximation, but it was not there in the options. So the right answer to this particular question is none of the above. So now let us go on to question 2. Consider steady developing laminar flow in a circular pipe. Which of the following statements is true for this flow? Velocity profile changes axially. Option 2, that is velocity profile changes radially. And option 3, pressure varies linearly in the axial direction. And fourth one, it is pressure remains constant. So reading the question carefully, first we'll understand what is being given. First one, it is steady flow, developing flow and laminar flow. Just clearly read the question. It is a steady flow, developing flow. It is not fully developed flow, but it is a developing flow and it is a laminar flow. So which of the following statements is true? Velocity profile changes axially. Second one, velocity profile changes radially. Third one, pressure varies linearly in the axial direction. And fourth, pressure remains constant. So answer, these are the options. From that we look at these are the statements. From that we look at the options. So first option is 1 and 2. Second one, it is 2 and 4. And option C, it is 2 and 3. Option D, it is 1 only. So we have 4 options and we need to identify the right option. So the right answer actually is option A is the right answer. So how we will see in the next slide, because as I mentioned, just read the question very carefully. It is mentioned steady state flow, developing flow and laminar flow. So this is just a profile I have taken from this paper, but the thing is we need to know only, we need to know only what is happening inside the system. So the first one is a velocity profile and second one is a pressure profile. So both are in a flow through a circular pipe, and it is giving us velocity variations and pressure variations, and both axial variation and radial variation is given. So now this is velocity and this is pressure. So now let us look at all the options step by step and see which is true, which is false. The first two statements are about velocity, next two are about pressure. So the first statement is velocity profile changes axially. So this is along the axial direction. So as we are able to see, it is a developing flow. So from this is the developing profile region, this is the fully developed flow region. In fully developed flow, it would be like a velocity profile would be like not varying, but in developing region, velocity profile changes axially. So that is true, because as we are able to see, there is a difference between axial velocity profile from here to this point. Like along axial direction, velocity profile is varying. So that is true. Second one, velocity profile changes radially. So again, radially there is a difference. It is not constant. So again, it is a true statement. So the first two statements regarding velocity are both true. The first one is velocity profile changes axially and velocity profile changes radially. Both the statements are true because we are in the fully developed, we are not in the fully developed region. We are in the developing region. So in the developing region, velocity profile changes radially and also velocity profile changes axially. Second, third one, pressure varies linearly in the axial direction. And this is the pressure variation profile, and we are in the developing region. Again, we are in this particular region, and the statement is that pressure varies linearly. So the linear variation we are not able to observe. Linear pressure drop we are able to observe in the developed flow region, but we are not able to observe the linear pressure drop in the we are not able to observe the linear pressure variation in the developing region. In developing region, till a certain point, the decrease is very high. After that, the decrease is very little compared to the initial zone. So, third statement is false. Last statement, pressure remains constant. So pressure is not remaining constant. So last statement is also false. So going back to the question, we are seeing consider steady developing laminar flow in a circular pipe. Which of the following statements is true for this flow? Velocity profile changes axially. That is true. Velocity profile changes radially. Again true. And pressure varies linearly in the axial direction. False. And fourth, pressure remains constant. False. So 1 and 2 are the right statements, which is given by option A. So answer is option A is the answer. So now we will go to question 3. In question 3, consider one-dimensional flow governed by d square u by dy square equal to c over a height h. Interval h is divided into 30 equal segments. Upper wall moves to the right at a speed of 1 meter per second while the lower wall is stationary. Number of discretized equations are. So this question is a direct application question of how many discretized equations we will be getting, and how many discretized points we will be getting, and how many discretized segments will be there. So just to help you visualize it, the problem is on a one-dimensional flow system. Consider a one-dimensional flow governed by this particular equation over a height h. So u is varying with respect to y, and that y is height. So this particular height, that is, you can keep it as a rod or something, and it is height h, and that particular thing is divided into 30 equal segments. And it is given that the upper wall moves at a speed of 1 meter per second, so lower wall is stationary. So mostly we know the value at the extremes right now, right? Upper wall is velocity at the u at h at y equal to h, we have velocity of 1 meter per second, and at y equal to 0, we have velocity of 0. Right. Now we are dividing that particular one-dimensional flow system into 30 segments, and we are asked for the number of discretized equations. So options are option A 29, option B 30, option C 31, option D 28. So anyone likes to answer the question can do. Okay, answer is actually 29 is the answer. Option A is the answer. Okay. Option A is the answer. That is 29 is the answer. So how we will see that? For example, we just take this segment alone. How many segments are there? We have divided it into three segments, three equal segments. And how many discretized points we have got? 1, 2, 3, 4. For dividing it a one-dimensional system into three equal segments, we have got 4 points. Of the 4 points, we know the value at the top, that is moving with 1 meter per second speed, and value at the bottom, it is stationary, so value is 0. So we have values at 2, and how many are we left with? We are left with 2. So it is 2 discretized equations we will be getting. These 2 discretized equations only we should solve. So consider the upper segment alone. We have 3 segments, 4 discretized points, 2 boundary points, top and bottom, and 2 interior nodes, for which discretized equations are written. I hope it is clear. So we have divided the segment into 3. Like, consider the upper segment alone, not the bottom one. This is just a full extension. But consider this system alone. We have 3 segments. 1, 2, 3. We have 3 equal segments, 4 discretized points, 2 boundary points, and 2 interior points. For the interior points only, we are writing the discretized equations for this system, because boundary values we know. For 30 segments, there will be 31 discretized points. For 3 segments, we have got 4 discretized points. So for 30 segments, there will be 31 discretized points. 2 boundary conditions. Velocity at upper wall and velocity at lower walls are given. So number of discretized equations becomes 31 minus 2, that is 29. That is the answer. So I hope it is you are clear now. We have 31 discretized points and 2 boundary points. So we are subtracting 2. 31 minus 2, it is giving us 29. So 29 is the right answer. Now let us move on to question 4. In question 4, the correct equation governing flow in a fully developed through a rectangular duct is dash. Correct equation governing flow in a fully developed rectangular duct is option A, dou square u by dou x square plus dou square v by dou y square equal to 1 by mu dp by dx. Option B, dou square u by dou y square plus dou square u by dou z square equal to 1 by mu dp by dx. Option C, dou square u by dou x square plus dou square u by dou y square equal to 1 by mu dp by dx. Option C, dou square w by dou x square plus dou square w by dou y square equal to minus 1 by mu dp by dx. So, can anyone answer this question? Answer is B actually. Option B is the right answer. So if you can say from what equations we have arrived at this formula, it would be fine. Like what equation we are simplifying to get this answer. We are simplifying the Navier-Stokes equation. So for fully developed flow through a rectangular duct, that is what is given in the question. Fully developed flow through a rectangular duct. So since it is a rectangular duct, we have XYZ coordinates, Cartesian coordinates, and it is a fully developed flow. So first we are considering the flow in an x direction. So if it is a flow in x direction, we have only x velocity left. That is u will be there and v and w components will be 0 and that u will be a function of y and z. I hope it is clear. So we are considering it in a flow in x direction and therefore v and w component, that is y component and z component velocity becomes 0 and u component x component velocity, that is u is the x component velocity, will be a function of y and z. Clear now? So now we are using the simplification in the Navier-Stokes equation. So Navier-Stokes equation in x direction is given by dou u by dou t plus u times of dou u by dou x plus v times of dou u by dou y plus w times of dou u by dou z equal to minus dou p by dou x plus rho gx plus mu into dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square. So it is a fully developed flow through a rectangular duct and we are considering the flow in the x direction. So u is a function of y and z, like steady state, and v and w component becomes 0. This becomes 0, v becomes 0, w becomes 0. And coming back, u is a function of y and z. So u variation with x is 0 and we are left with this one and this body force we are not considering for now and this again becomes 0. So it is 0 equal to minus dou p by dou x plus mu times of dou square u by dou y square plus dou square u by dou z square. So this term and that term goes to the other side. Mu also goes to the other side. Dou square u by dou y square plus dou square u by dou z square equal to 1 by mu into dou p by dou x. This dou p by dou x goes that side and we will be left with this and later mu also goes to the other side. So therefore dou square u by dou y square plus dou square u by dou z square equal to 1 by mu dou p by dou x. So coming back to the question, the right answer is correct equation governing flow in a fully developed flow through a rectangular duct is given by dou square u by dou y square plus dou square u by dou z square equal to 1 by mu dou p by dou x. So that is the equation. So why we are taking x direction is that mostly pressure is given in the x direction. We can take it in v or w direction also depending on what is given in the question and what is given in the options. But here since it is like x directional flow, we are considering everything in x basis. On that basis, by reading the question itself, you can reject certain options. For example, it is an x directional flow. So mostly it would be, you would be knowing that only that component varies with respect to y and z. So here it is other two. So if it is u, it would be like y and z, and therefore there would not be any variation. So it would be 0, and v again like it also 0. V and W, like because it is X, V and W will be 0 for this particular case, actually not for everywhere. I am talking about this particular case. So this we can reject, and again this is W is varying with X and Y, but here it is dp by dx. So again it is a false statement. So in that manner, we can reject few options clearly and come to the conclusion as well. Answer is option B. Now we will go to question 5. Consider fully developed laminar flow through a square duct of side L and that through a rectangular duct with to height ratio of 2 such that both of them have the same cross-sectional area. If the same fluid flows through both the ducts at the same volumetric flow, which of the following statements is true about the both the flows? Option 1, governing partial differential equation is the same. Second one, wall boundary conditions are the same, though these are applied at different locations. Option 3, statement 3, flow domain is the same. Excuse me. Option statement 3, flow domain is the same. So what is given? It is given that we are considering a system with fully developed flow, that is laminar flow through a square duct and through a rectangular duct. We have two cases over here. First one is square flow through a square duct. Second one is flow through a rectangular duct. The square duct has side L and rectangular duct has width to height ratio of 2. So if width is 2 times of height. If height is L, width is 2L. In that case, and both of them have the same cross sectional area. So the cross sectional area is same. So depending on that, the dimensions will be adjusted. If the same fluid flows through both the ducts at the same volumetric flow, which of the following statements is true? So for that only we are given three statements. First one is governing partial differential equation is the same. And second one, wall boundary conditions are the same, though these are applied at different locations. Last one, flow domain is the same. So first option 1 only, option B 2 only, option C 1 and 2 only, option D 1, 2 and 3. Answer is option C 1 and 2 only. Why? Because first one it is mentioning about governing partial differential equation. So we are clear that we have a square duct and we have a rectangular duct. In this, both of them have the same cross sectional area, but square duct has length L and rectangular duct has width to height ratio of 2. So for example, if I'll give you a small problem. If area of square duct is L cross L, that is cross sectional area, that is becomes L square, and rectangular cross section, what it becomes, it has length to width to height ratio as 2. So it becomes width into height, width is equal to 2 height into h is equal to 3h square. L square is equal to 3h square. So h is equal to L by 3 root. So both of them have the same cross sectional area. So what is coming is that I did a small calculation for you to give to give you an idea. So square duct has a side L and the same cross sectional area is there in the rectangular duct, and rectangular duct has width to height ratio of 2. So if we do the calculation on the basis that both of them have the same cross sectional area, we are getting the height of the rectangular duct as square root of length divided by 3. Length divided by 3, the square root gives us height, and width is twice that. So we are clear of the aspects or the coordinates of the square duct as well as the rectangular duct. So now coming back to the options statements, first is governing partial differential equation is the same. If it is square duct or rectangular duct, what are the equations we are solving? We are solving the continuity equation and Navier-Stokes equations. and both of them are in Cartesian coordinates as well, and also the governing partial differential equation, therefore it is the same. So 1 is 2. Second one, wall boundary conditions are the same, though these are applied at different locations. Boundary conditions will be the same, right? If it is moving and if it is moving. If it is not moving, it is not moving. So we can give that. Inlet also the volumetric flow, the flow is the same volumetric flow. So the location of the boundary condition may be different because the dimensions of square and rectangular duct are different. The boundary condition location will be different, but the condition will be the same. So the wall boundary conditions are the same, though these are applied at different locations. Third statement, it is flow domain is the same. Flow domain is not the same actually. Here it is a square duct and here it is a rectangular duct, and flow domain, it is like varying. You can imagine, right? Here the flow is in the square duct flow and here it is in the rectangular duct, and the dimensions of which both of them are not agreeing as well because of the condition that cross sectional area is the same. So both of them are different as well. So flow domain is not the same. So therefore options, statements 1 and 2 are right. So option C is the right answer. Hope it is clear now. Now let us go on to question 6. And okay, from here on some 7 problems will be like some theory questions only, I guess. So the first one is, and then later on we'll have some interesting problems. So first one is, so we'll quickly rush up the 7 problems. So it will be like we'll have plenty of time to solve 15 problems there. So the ideal fluid, what is an ideal fluid? Ideal fluid is the one obeys ideal gas law, or it has constant thermophysical properties, or option C has zero viscosity, option D none of the above. So when we are talking about ideal fluid, we are talking about the fluid which has zero viscosity. In practical it is not existent, but it is, for that name only, it is an ideal fluid. So answer is option C. These are the practice problems I have taken from week 0 content, I guess. So you can check that as well if you are interested. So question 7 is, example of a Newtonian fluid is dash. Option A air, option B mercury, option C glycerin, option D all of the above. All of the above is the answer because most of the fluids will be Newtonian fluid. Like I'm not talking about those paste, those sand mixture, cornstarch. I'm not talking about, but pure fluids which we can represent through some chemical formula. That is what the definition we have studied. The fluid for which we can represent it through a chemical structure and chemical formula, and air is the only Newtonian fluid. So all of the above is the right answer. Now question 8. Boundary layer flow approximation applies to, mostly it will be applied to when Reynolds number is higher, like turbulent flow cases. Option A only to very low Reynolds number, false. Option B only to high Reynolds number but still laminar flows. This is again true because we are applying to high Reynolds number cases. And option C, it is only to turbulent flows. Option D, to both B and C. Both B and C is the right answer. To high Reynolds number but still laminar case, and to turbulent flows. So both B and C is the right answer. Option D is the right answer. And moving on to question 9, we have which of the following contributes to viscous drag in flow over sphere? So only wall shear, option B only pressure variation, and option C both, option D neither. So flow, we have a viscous drag in a flow over a sphere. So what are all the contributions for that viscous drag? The first one is wall shear and the second one is pressure variation. So obviously pressure variation is one cause, and also since it is a flow over sphere and that too viscous flow over sphere, we have wall shear as well. So both of them is the right answer. Option C is the right answer. Now moving on to question 10. Okay, I shouldn't have given this, but still, in a laminar fully developed flow through a pipe, here read the question carefully, it is fully developed flow through a pipe. Option A, axial pressure variation is linear. Option B, radial pressure profile is linear. Option C, radial pressure profile is parabolic. Option D, pressure is constant. So what is the answer? Option A is the answer, because we have seen this in the last question itself, where axial pressure variation we have seen. So axial pressure variation is linear. So linear pressure drop in fully developed region. So that's what I asked you to read the question carefully. In the previous question it was about developing flow. Here it is fully developed flow. So that is the difference. And laminar fully developed flow through a pipe, the axial pressure variation is linear. Option A is the right answer. Coming to question 11, we have question 11. In steady incompressible flow through converging diverging nozzle, pressure at the exit section is dash. Option A, highest. Option B, lowest. Option C, lower than the inlet. Option D, same as the inlet. So we are dealing with the steady flow as well as the incompressible flow through a converging diverging nozzle. So at the diverging section, obviously area will be high, and therefore the pressure at the exit section is lower than the inlet is the right answer. So option C is the right answer. Coming to question 12, we have over 50% of the time spent in the industry on a CFD project is devoted to the definition of the domain geometry and grid generation. Which one will be the reason for this? So as I mentioned, when we are dealing with CFD problems, I'm talking about we are getting the solution for some systems. At that time, we spend more than 50% of the time in getting the doing pre-processing, wherein we define the domain geometry and generating the grids, that is the mesh. Why later on the getting solution would be like time consuming one only, I'm not talking about that, but that would be comparatively better. But most of the time it would be like time would be involved in generating the mesh, that to proper mesh. It is not about generating mesh, but it is about generating the proper mesh. Which one will be the reason for this? Option A, more grids will give better results. Option B, calculation time is directly proportional to number of cells. To generate non-uniform grids. To generate an optimal grid, which is a compromise between desired accuracy and solution cost. So what do you think is the reason that we are spending over 50% of the time on like domain geometry and grid generation? What would be the reason you guys think? Okay, the answer is actually to generate an optimal grid wherein it is a compromise between desired accuracy and solution cost. It is not always that we go with a very fine mesh. Most of the, we do that grid independence test, wherein after certain refinement, the solution would not be changing much. So that would be like optimal one. And also in certain cases, uh, we require uniform grids, and time also matters. It is not always that we require accuracy. Certain times we have to make a compromise between the time and accuracy. So that solution cost is like involving all those factors, and therefore optimal grid is essential. Like after, as I mentioned now, like after a certain refinement there would not be any change in the solution. So it is sufficient if we go with that particular grids. So to generate an optimal grid, which is a compromise between desired accuracy and solution cost, option D is the right answer. And question 13, it is about in turbulent flow through a rectangular channel, flow rate is double. The pressure gradient is likely to dash. In turbulent flow through a rectangular channel, flow rate is double, pressure gradient is likely to dash. So what happens to pressure gradient if we double the flow rate? So I'll give you the options. Option A remains the same. Option B double. Option C quadruple. Option D be 16 times higher. What is your guess on this particular problem? Answer is actually quadruple. Quadruple is the answer. Okay. Quadruple is the answer. Option C. How pressure gradient and delta P by L equal to FD into friction factor into rho into V square by D. V is like a factor of flow rate, function of flow rate. So if flow rate is double, it is like, since it is a square, it is 2 times 2 2s are 4. So pressure gradient is likely to quadruple. Option C is the right answer. So now we are moving to sample problems. Okay. So in sample problems, how it is that the format is we have one case followed by few problems. So first we'll read the case and later we'll solve the problems. So here I guess it is some 13, 15 problems are there, I guess. So most of them are like direct observation, direct reading, and some few conceptual questions are there. So we'll see them and pay attention to these problems because your assignment problems are mostly a reflection of these problems. A reflection in sense like similar problems will be there. So pay attention from here on. So first one, the case, we'll read the case first. Choose the correct answers from the options below for this particular case. You wish to solve a problem involving steady state heat conduction in a slab of thickness L. The wall has volumetric heat generation rate Q. If height and breadth of slab are very large compared to L, then one can assume the problem to be one-dimensional. For the case of constant thermal conductivity, the equation governing temperature distribution takes the form K into d square T by dy square equal to Q. K is the thermal conductivity, T is the temperature, Y is the distance in thickness, Y is the distance in the thickness direction from the end of the wall, and Q is the volumetric heat generation rate. For this case, the calculation domain encompasses the region y equal to 0, L with both boundaries included in the calculation domain. Just okay. Okay. Okay, first let us list down what are all the things given in the problem. So the first thing is that we are solving a steady state heat conduction problem. It is important, steady state heat conduction in a slab of thickness L. The volumetric heat generation rate is Q. If height and breadth of the slab are very large compared to L, one can assume the problem to be one-dimensional. So slab thickness is very small when compared to that. So the problem we are assuming height is like very large. So we are assuming uh, one-dimensional problem, and thermal conductivity here it is assumed constant. I mean not assumed, but here it is taken constant. For case of constant thermal conductivity, equation governing temperature distribution takes the form Q is equal to K into d square T by dy square. Read carefully the question. Thermal conductivity is constant. I am stressing these points because the questions to come has all these things. So whenever you are reading case, read all the statements thoroughly. So the problem questions will have hints from these statements only. So Q is equal to K into d square T by dy square, where K is the thermal conductivity and it is a constant thermal conductivity, and T is the temperature, Y is the distance in thickness, direction from one end of the wall, and Q is the volumetric heat generation rate. Calculation domain encompasses Y in 0 to L with both boundaries included in the calculation domain. So which of the following cases is not permitted by equation 1? First one, a thermal conductivity is dependent on temperature. Thermal conductivity is dependent on location inside the calculation domain. Option C, both. Option D, neither. So in the question itself, it is mentioned in caps. So which of the following cases is not permitted by equation 1? So, and options are thermal conductivity, that is K. K is dependent on temperature, and second statement, K is dependent on location inside the domain. Which statement do you think is not permitted, or do you think both of them are permitted or both of them are not permitted? You can say the answer as well, but if you can give explanation, that would be better. Anyone wish to take a chance? Okay, since this is the first class, let it be, but if you can answer it would be well and good. But yeah, Q, that is K is the thermal conductivity, and it is both of the statements are not permitted by the equation 1. Why? Because as I mentioned in the while reading the K statement itself, K Q is equal to K into d square T by dy square is the equation applicable when K is constant. If K is varying, that is not the case. So K is constant. If K is constant, it is not dependent on temperature and it is not dependent on location inside the calculation domain. So both of the statements are not permitted by equation 1. So answer is option C. Option C is the right answer. Both of the statements are not permitted. Read the question carefully again and again I am saying. So now we'll go to question 2. Okay, explanation is that above equation is given for the case of constant thermal conductivity. To include variation of K with either T or Y or both, equation should be written as d by dy into K dt by dy. That is, K comes inside the equation and it equal to Q. So that is there. So we have not written the equation in such a form, so K is, because K is used as a constant in that equation, so K is not a dependent on temperature or position. So I hope it is clear. Now coming to question 2, for equation 1 to be dimensionally consistent, units of Q should be dash. So we have written the equation Q is equal to K into d square T by dy square. So what is the unit of Q for equation 1 to be dimensionally consistent? Option A, it is kg meter per second square. Option B, kg by meter second cube. Option C, kg meter per second square. Option D, kg meter square by second cube. Answer is option B is right answer. Kg by meter second cube. Why and not why? How? We need to do the unit dimensionally. We need to arrive at the unit. So given equation is q is equal to k into d square t by dy square. Units for the known variables, first we should identify. K is the thermal conductivity. So as we all know, the unit of K as watt per meter Kelvin, and T is Kelvin and Y is meter. So we are substituting all the known units in the equation and getting the unknown unit. So Q unit is equal to watt per meter Kelvin, that is K unit, into d square T by dy square, that is K by meter square. So K get cancelled and it is watt per meter cube. And what is the unit of watts? It is joules per second is watts. So it is joules per second divided by meter cube. And what is the unit of joules? It is Newton meter. Newton meter per second divided by meter cube. Newton unit is kg meter per second square into meter per second. So meter square it becomes, and divided by meter cube. So 1 meter remains, and here second square and second, it becomes second cube. So kg by meter second cube. So answer is kg by meter second cube. So option B is the right answer. For equation 1 to be dimensionally consistent, units of Q should be kg by meter second cube. So I hope it is clear now. For equation 1 to be dimensionally consistent, units of Q should be kg by meter second cube. Clear? So now we will go to question 3. Admissible forms of Q in equation 1 are. Again, admissible form of Q. So Q is equal to K into d square T by dy square. What are all the admissible forms of Q? So Q is constant, Q is a function of T, and Q is a function of Y. So what do you think is the answer? So I'll give the options first. Options are A, 1 only. Option B, 1 and 2 only. Option C, 1 and 3 only. Option D, 1, 2 and 3. So what is the admissible form of Q in equation 1? I am reminding the equation 1. Equation 1 is nothing but Q is equal to K into d square T by dy square. So from the function itself, we can say that Q is a function of T as well as Q is a function of Y. And Q is a constant. Can be admissible forms of Q in equation 1. It can be constant because K again is constant. Q is equal to K into d square T by dy square. So Q can be a function of T, Q can be a function of Y, and Q can be constant also. So option D is the right answer. Option D, 1, 2 and 3 is the right answer. So now let us go on to question 4. Just a one line explanation. Since form of Q has not been mentioned, it can be a function of T and Y. K needs to be constant. Like even though Q can be a function of T and Y, K needs to be constant. Thermal conductivity is not a function of T or Y. That is what we saw in the first question, right? Thermal conductivity is not dependent on temperature or position, but Q can be dependent on temperature or position, or it can be constant also. Just keep that in mind. Okay. Question 4. Okay. Question 4. Which of the following are applicable boundary conditions for equation 1? Option 1. Temperature at y equal to 0 equal to A, and temperature at y equal to L equal to B, where A and B are constants. Temperature at temperature gradient dt by dy at y equal to 0 is equal to c, and dt by dy at y equal to l equal to d, where again c and d are constants. And last is third statement is that temperature gradient, that is dt by dy at y equal to 0 is equal to E, and pure temperature value at y equal to F, sorry, y equal to 0 is F. So we have been saying like, if you remember in the one dimensional problem we have told like how many discretized equations we will get. In that problem we have mentioned that we will be using boundary conditions, so 2 points will be eliminated in that. So mostly like boundary points we know the answers, right? So this question is about what are the applicable boundary conditions, so what can be the permissible ones. So we'll see 1, 2 and 3 statements first and see which can be applicable and which cannot be. First one, it is t at y equal to 0 is E. So if we look at it, this is y equal to 0 and this at y equal to L. Y equal to 0, y equal to L. Temperature at y equal to 0 is A, temperature at y equal to L is B. Okay, here. This is applicable, right? Because we know the temperature value at both the points. This is an applicable boundary condition. Second one, it is given that temperature gradient at y equal to 0 is C and temperature gradient at y equal to y equal to L is D. One thing is that we either use both the values constant, both the variable values we need to identify. How to say, like we have two boundary points, right? Now we have two boundary points. The permissible ones are in boundary conditions we generally specify the value of the variables, or we specify the value of the gradients, flex or whatever. So mostly one condition will be, at least one condition should be value of the variables. Mostly two conditions would not be specified as the gradient condition. For example, in this particular problem, statement 2, it is dt by dy at y equal to 0 is given and dt by dy at y equal to L is also given. So mostly both the boundary points would not be preferred to have gradient values, because it won't give us unique solutions. Unique solutions we won't be getting. That is the reason. And third one, it is dt by dy at y equal to 0 is E, and dt at y equal to 0 is F. Again, here what is the mistake? Can anyone identify? It is because y equal to 0, both the conditions are at y equal to 0. So it is not applicable. So only first statement is true. So we'll now look at the options and identify the correct option. Option A, 1 only. Option B, 1 and 2. Option C, 1 and 3 only. Option D, 1, 2 and 3. So answer is, as we mentioned, it is option A, that is 1 only is the right answer. Option A, 1 only is the right answer. So option A is the right answer. Now we will see why. Specification of the boundary condition at both ends is essential. At both the ends we need to specify the boundary conditions. Therefore option 3 is incorrect. Specification of only derivative boundary condition at both ends will not give a unique solutions. These both are derivative boundary conditions. At both the ends, if we are using derivative, it won't give us a unique solution. So option 2 is incorrect as well. So answer is option A, which is 1 only. Now we will go to question 5. In question 5, what do we have? We have For equation 1 to be used for finding the temperature distribution along the length of the rod, which of the following conditions must be met? Rod must have L by D very much greater than 1, where L and D are length and diameter of the rod. The rod must have its curved side insulated. The rod must have a rectangular cross section. So coming back to equation 1, it was nothing but Q is equal to K into D square T by dy square. It is a one-dimensional equation, right? Q is a function of, even though it is varying with T, it is a varying with Y only. So we are using it to find the temperature distribution along the length of the rod. So when we are using that, what are all the conditions that should be met? So one condition is that we are finding the temperature distribution along the length of the rod. So it must be a one-dimensional rod. When it would be one-dimensional, when length is very larger than the diameter, we can use it as a one-dimensional. So that is what is given in the statement 1. The rod must have L by D ratio very greater than 1. That is, length is very much greater than D, where L is the length of the rod and D is the diameter of the rod. And rod must have its curved side insulated, and rod must have rectangular cross section. These are not essential statements. Rod can have curved side insulated or not, because if it is insulated, we can see that temperature would be, values would be known. I mean, gradient values can be known, but curve, rectangular cross section or circular cross section, it doesn't matter. We can modify the equations accordingly, but to use the equation as a one-dimensional equation, we need to have the length of the rod very much greater than the diameter of the rod. So option 1 only is the statement 1 is alone right. So option A 1 only, option B 1 and 2 only, option C 1 and 3 only, option D 1, 2 and 3. So as we have seen that right answer is option A 1 only is the right answer. I hope it is clear. Option A 1 only is the right answer. Because equation is one dimensional and is appropriate for case thickness is larger than the width and the height. L by W is greater than 1 and L by H is greater than 1. Possibility of heat loss along the length can be included in the specification of Q. Actually, the statement, it is just a if the length is very large. I mean, one dimension, it is larger than the other two dimensions. That is the takeaway. Just don't mind the variables being used, whether it is height or thickness or width, whatever it is. One dimension, it is larger than the other two dimensions. Now we have question 5. We have okay. Now we have question 6. So Just give me 2 minutes break. I'll come back. So we'll start again. Question 6 it is about. So which of the following is an admissible extension of equation 1 to steady heat conduction in 2 dimensions? Statement 1, dou square t by dou y square plus dou square t by dou z square is equal to 100. Option 2, it is dou square t by dou x square plus dou square t by dou y square is equal to 3 times of x square y. It is third one, dou t by dou t equal to alpha times dou square t by dou x square, where alpha is greater than 0. And option A, it is 1 only. Option B, it is 1 and 2 only. Option C, 1, 2 and 3. Option D, none of the above. Answer is actually option C, 1, 2 and 3, because option 1 and 2 are clearly admissible. Dou square t by dou x square plus dou square t by dou z square equal to 100. And similarly, dou square t by x square, dou x square plus dou square t by dou y square equal to 3x square y. So both are clearly 2 dimension. And option 3 is 1 dimensional in space, but mathematically t also we can use it as a function of x and t. So mathematically 2 dimension. So that is why answer is option C. And moving on to question 7, we have, which of the following statements is true about the use of finite difference approximations for solving CFD problems? So in the first few problems also, in one problem we have seen use the finite difference approximation. Forward difference, backward difference, central difference, those things we have used. So in the given statements, which of the statements is true about the use of finite difference approximations for solving CFD problems? So the first statement is finite difference approximation can be applied to problems described in cylindrical coordinate system. Second one, for a given partial differential equation PDE, there is only one correct finite difference approximation. Third one, finite difference approximation at a point converts a PDE into an algebraic equation. So these are the three statements. So first we look at the statements. Finite difference approximation can be applied to problems in cylindrical coordinates. Yeah, we can apply it to problems in cylindrical coordinates as well. Second, so first statement is true. Second statement, for a given partial differential equation, there is only one correct FD approximation. This is false because we can use different approximations. Like the method can be different. If we can use forward difference approach, we can use backward difference approach, we can use central difference approach, whatever it can be, but it can be used. So it is false that for the given PDE we have only one correct FD approximation is a false statement. So third statement, it is FD approximation at a point converts a PDE into an algebraic equation. So finite difference converts a point PDE into an algebraic equation. That is a true statement. Because if you remember, we have dou square u by dou y square, we have written it as u at I comma j minus u 2 times of u at I comma j plus u times u at I comma j plus 1 divided by 2 times of delta y square. So the right hand side equation is an algebraic equation, can be solved as an algebraic equation. So third statement is also true. So except second statement, first and third are right. So we look at the options now. Option A 1 only, option B 1 and 2, option C 1 and 3, option D 1, 2 and 3. So answer is 1 and 3 only. So option C is the right statement, right answer. Option C 1 and 3 only is the right answer. So the finite difference approximation can be forward difference, backward difference and central difference approximations. So that is, we have seen in the first 5 problems. One of the problem was this. And now we will move to question 8. In question 8, which of the following statements is true about the use of finite difference approximations for solving a given partial differential equation? FD approximation of a PDE is applied at all grid points. Second one, same FD approximation must be applied at all points in a domain. Okay. Can anyone give the answer for this actually? Or else I'll tell the answer, you people can say why. Which of the following statements is true about the use of FD approximation? So when we are using FD approximations for solving the partial differential equations, which of the following statements is true? First one, it is FD approximation of a PDE is applied at all grid points. This is false. And second one, same FD approximation must be applied at all points in a domain. So this is false as well. So option A 1 only, option B 2 only, option C 1 and 2, option D neither 1 nor 2. So option D is the right answer, neither 1 nor 2. So why? Because FD approximation of the PDE is applied at all points. Are we applying FD approximation at all grid points? No, right? Which are the points we are excluding? We are excluding the boundary points. The boundary points, if you remember, boundary conditions we are using and we know the values or we know the gradient, or somehow we are not applying the FD approximations, we are using the boundary conditions. Second one, it is same FD approximation must be applied at all points in a domain. Again, we are not using the same FD approximation at all points. The schemes can be different depending on the system under consideration and the grid generated. Different FD approximation can be used. Like one corner we can use forward difference scheme, other corner we can use other schemes as well, backward or central or whatever. So neither 1 nor 2 is the right answer. The finite difference approximations applied to the interior grid points. For boundary points, boundary conditions are used to derive the algebraic equations. If it is a direct value specifying the direct variable, we know the value. or else we are not approximating use to interior grid points, rather than we are using boundary conditions, uh, and the we like gradients, derivatives. If we are using that two conditions to derive the algebraic equations. So the Dirichlet and boundary condition is the specification of direct values, and non-Dirichlet is like mixed boundary conditions. We have so many types of boundary conditions. We have all those things you will study in later classes. But for now, if there are two types of boundary conditions, one is specifying the value of the variable directly, and the other one is giving the derivative of the variable at that point. So two conditions are met. So these two are basics. Other types, mixed ones, those Newman boundary condition is what where we specify the derivatives, and mixed condition or combination condition, all those things you will be studying later, so don't worry about that. So for now, it is boundary conditions are used to derive algebraic equations. So we are not using the boundary conditions at the, sorry, we are not using the FD approximation at the boundary conditions, and same FD approximation must be applied at all points in a domain is also false. So neither 1 nor 2 is the answer. Question 9. Consider the Laplace equation in a two-dimensional rectangular domain with Dirichlet boundary condition. The equation is discretized at all interior points using second order accurate finite difference approximations with uniform grid spacing in both directions. Which of the following statement is true about the resulting set of algebraic equations? So we have a Laplace boundary conditions, Laplace equations, and it is in a two-dimensional rectangular domain, and we are using Dirichlet boundary condition, and we are discretizing the equation at all interior grid points using the second order accurate finite difference schemes, and uniform grid spacing is maintained in both the directions x and y or whatever it is. Which of the following statements is true about the resulting set of algebraic equations? Each algebraic equations will have exactly 5 non-zero coefficients. Statement 1. Statement 2. Each algebraic equation will have at most 5 non-zero coefficients. There will be at least one equation with only one non-zero coefficient. Okay, 3 statements are given. So actually Laplace equation, if you remember, it is dou square u by dou x square plus dou square u by dou y square, something like that, or dou square f by, we'll keep it f, some random function, dou square f by dou x square plus dou square f by dou y square is equal to something. So f is a second order partial differential equation. So if we are converting it, if you remember the first derivative we did, we are using I minus 1 point, ith point, I plus 1th point. Similarly, for y direction, we are using j minus 1th point, jth point, j plus 1th point. So we have 5 points total. So in the interior grids, we have 5 points, whereas in the boundary conditions, if you remember, the boundary values might be specified, so those might not account. So these 5 points will give 5 coefficients. So at the max, we can have 5 non-zero coefficients. Minimum it can be whatever, but maximum it can be 5 non-zero coefficients. So coming back, each algebraic equation will have exactly 5 non-zero coefficients. It is not exactly. Why? Because in the boundaries we know the values, we cannot use it in the as a coefficient. And second one, each algebraic equation will have at most 5 non-zero coefficients. At the maximum we can have 5 non-zero coefficients. That is true. So second statement is true. Third one, again coming back, there will be at least one equation with only one non-zero coefficient. Again this is false, because we do not know that, like mostly that won't be the case. So one non-zero coefficient even in the boundaries, if we use, it would be like 2 or 3 minus, but only one we can't say. So second statement only is true. So coming to the options, option A 1 only, option B 2 only, option C 3 only, option D 1, 2 and 3. The answer is option B 2 only is the right answer because we'll have at most 5 non-zero coefficients. Why? Because Laplace equation is nothing but dou square f by dou x square plus dou square f by dou y square. We are using second order accurate finite difference approximations. So for the x derivative alone, dou square f by dou x square, we will be using the points I minus 1, ith point, I plus 1th point. Similarly for j point, j minus 1, jth point, j plus 1 point. Or else I'll go back and show you. I don't know which slide it was. We had one domain, right? I'm talking about this only. So we have dou square f by dou x square plus dou square f by dou y square. So dou square f by dou x square, we have dou y square, we have 3 points. That is j plus 1 point, j point, j minus 1 point. So these are all the coefficients we will have. And here if we take for the similar case for the x domain, x direction, we have I minus 1, I plus 1. So we have 1, 2, 3, 4 and 5. So maximum it can be 5. But depending on the boundary, it can reduce as well. So that is why we are saying at most it can be 5. So maximum it can have 5 non-zero coefficients. Only. The grid point Tij for second order approximation will have variables I minus 1 comma j, I plus 1 comma j, I comma j minus 1, I comma j plus 1. So option 2 is the correct answer. So that is what we have seen. Okay. At boundaries, number of non-zero coefficients is often lower. So we can say at max it will have 5 non-zero coefficients. Will implied resulting matrix equation is reducible. Such points can be taken out of the matrix equations. So that is why resulting matrix equation is reducible. That is only one max. I mean it will have exactly one, it was mentioned, right? If that is the case, points can be taken out of the matrix equation. So that again is not feasible. I mean not practical. So question 10. Which of the following statements is true about the Gauss-Seidel iterative method for the solution of algebraic equations resulting from the discretization of linear Laplace equations? So for now we have been saying we will be discretizing the Laplace equation or partial differential equation. We are discretizing it and converting it into an algebraic equation, right? And from the resulting algebraic equation, how will we solve? So we are using numerical methods. That's what I mentioned in the first initial slides itself, that CFD requires the knowledge of physics of the system as well as we need to know mathematical concepts like numerical methods we will be applying. So Gauss-Seidel iterative method for the solution of algebraic equations resulting from the discretization of linear Laplace equation. So first one, the method will always converge. Second one, initial guess at one grid point is sufficient for the method to get started. Option 3, method will approach the exact solution asymptotically. So the first one is method will always converge. I mean if the conditions are proper, method will converge. And second statement, so first statement is true. Second statement, initial guess at one grid point is sufficient for the method to get started. Gauss-Seidel method, if you guys remember from your numerical methods class, we need initial guess for all the grid points. So second statement is false. And third statement, the method will exactly approach the exact solution asymptotically. So third statement is also false. I mean third statement is true. Sorry, third statement is true. It will approach the solution asymptotically. The solution might not be exact, like after so many large number of iterations, it will be approaching very near to the solution. So first one, option A 1 only, option B 1 and 2 only, option C 1 and 3 only, option D 1, 2 and 3. So now we know the answer is option D, 1, 2 and 3 is the right answer. Oh, so I mean, sorry, not option D, 1 and 3. Option C is the right answer because we have clearly seen that initial guess at one grid point is not sufficient. We need to have the initial grid point at all the initial guess at all the grid points. Initial guess at all grid points must be known, because Gauss-Seidel method requires initial guesses for all the variables, as these equations needs to be solved simultaneously and are not reducible. So we are solving the equations simultaneously, so we need to know initial guess for all the variables. Alright, now we will go to question 11. Which of the following statements is true about Gauss-Seidel iterative method for the solution of algebraic equations resulting from the discretization of linear Laplace equation? So Gauss-Seidel iterative method we are using. Which of the following statements is true? First one, GS method is only method that can be used. Second one, GS method is the best of the available methods. So the question itself is very simple. We can say it is not the only method, as well as it is not the best method also. Option A, 1 only. Option B, 2 only. Option C, 1 and 2. Option D, neither 1 nor 2. So the question is about which of the statements is true. So answer is option D, neither 1 nor 2. Both the statements are false. There are n number of numerical methods available, and there are better methods to give the solutions as well. The computational expense might be higher in those cases, but still there are numerous methods available, and there are methods that will give better solution than Gauss-Seidel method also. So there are many methods and there are better methods as well. So I hope it is clear now. Now we'll go to question 12. You wish to solve a set of linear algebraic equations written in the form of Ax is equal to b using the Gauss-Seidel method. Which of the following should you have in your computer program? So as I mentioned, we are converting the what do we call partial differential equation into algebraic equation, and using numerical methods to solve the algebraic equation. So when we are solving the numerical equation using numerical method, we obviously go for the computer program, right? So what are all the conditions that we will be implementing there? Can anyone say that? When we are using Gauss-Seidel method, what are all the conditions we will be implementing? We will see the options as well. First one, check for diagonal dominance. Second one, stopping criteria. Third one, iteration count. So option A, 1 and 2. Option B, 1 and 3. Option C, 2 and 3. Option D, 1, 2 and 3. So answer is that option D is the right answer, 1, 2 and 3. Why? Because when we are writing a program to solve the Gauss-Seidel, solve the equations using Gauss-Seidel method, we need to have the diagonal dominance check. Only then we will get the proper solution, and only then we can proceed. So diagonal dominance check is a properly needed check we require. And second one is a stopping criteria. When do we need to stop the simulation? When tolerance is below this, or when something like it should not be running in a continuous loop, right? There should be somewhere the program needs to be stopped. When the relative error on the error percentage is below the critical value, below the tolerance value, those type of stopping criteria we need to have. And also iteration count, like it will be running, we need to have an iteration count to make the performance better or whatever, but we need to have it as well. So 1, 2 and 3 are essential. Option D, 1, 2 and 3, these are essential checks for the general case of attempting Gauss-Seidel for Ax is equal to b. Question 13. Which of the following can be considered as a strong point of CFD approach as compared to analytical methods to solving fluid flow problems? Option A, range of problems that can be analyzed. Option B, reasonably correctness of predicted solution. Option C, option 3 is ease of solution. What are the right ones from here? Option A, all 3. Option B, 1 and 2 only. Option C, 1 and 3 only. Option D, 1 only. So this question and next question are almost similar. So in the initial thing itself, while we were reading what is the computational fluid dynamics and why is it required, we have been saying few things in comparison to theoretical fluid dynamics. So one thing is that it is not always possible to get the solution through analytical approach. That is why we are using the CFD approach. So the first statement, range of problems that can be analyzed. Yes, it is a true. Like we can, in the time we are using to get the analytical solutions, it might or might not be possible. We might not get as well. So, strong point of CFD approach, range of problems that can be analyzed. It is the advantage of CFD. Second one, reasonable correctness of the predicted solution. The predicted solution will have reasonable correctness. It might not be the perfect solution or the best solution like which we are obtaining through analytical methods. Analytical methods obviously will give the exact solution, but these solution from CFD will give a closer predictions. And third, ease of solution. um, it is not easier to get the solution through CFD approach. It involves a lot of computational cost, lot of time needs to be spent in grid generation. Those things are there. So 1 and 2 only is the right answer. We'll check it once as well. Yeah, option B, 1 and 2 only right statements, because ease of solution, it is not easier to get solutions through CFD. We need to spend a lot of computational power, we need to spend a lot of time in grid generation, and we need to identify the right solvers. So many things are there, and the simulations also will take a lot and lot of time to get the solution. So 1 and 2 is only the right statement. Similar question, analytical solutions are far easier to use than CFD. So in comparison with CFD and analytical approach, analytical solutions, if available, that is the point over here. If it is available, analytical solutions are easier to use. But will it be available? That is a question. Or will it be available all the time? I'm not talking about. I'm not saying it won't be available, but I'm saying like it won't be available all the time for all the applications, all the problems. So that is the case. So we are nearing the last two problems. This problem is similar to question 13. Which of the following can be considered as a weak point of CFD approach as compared to analytical methods to solving fluid flow problems? Option 1, range of problems that can be analyzed. Second statement, reasonable correctness of the predicted solution. Third one, ease of solution. So option A, all three. Option B, 1 and 2. Option C, 2 and 3. Option D, 3 only. Option E, none. So in the previous question, it was asked which is the advantage of CFD when compared to analytical approach. So 1 and 2 statements were used. But here, which is the weaker point of CFD when compared to analytical methods? So answer is ease of solution. So option 3 is the right answer, because analytical approach, if available, are easier. While CFD, that is not the case. 3 only is the right answer. So coming to the last question of today's session. So question 15, which of the following need not to be known to solve a fluid flow problem using CFD approach? Option, statements, whatever. Friction factor, second Reynolds number, third one viscosity. Option A, all three. Option B, 1 and 2. Option C, 2 and 3. Option D, 1 only. So read the question carefully. It is asking about which of the following need not be known to solve a fluid flow problem using CFD approach. The first one is friction factor. When we are using CFD approach, we need not know the friction factor value. So it is used in the analytical solutions, but in friction factor in CFD is not required. Second one, it is a Reynolds number. Again, Reynolds number we do not require. Rather, we are calculating it from the solutions, from the CFD solutions. We can calculate Reynolds number if and when needed, but we need not know it prior. We need not know it to solve a fluid flow problem. Reynolds number need not be known. And third is viscosity. Viscosity we need to know. Fluid properties we need to know. Density, viscosity, those terms come in Navier-Stokes equations. If you remember the Navier-Stokes equations, in the right hand side we have mu into dou square u by dou x plus dou square u by dou y square plus dou square u by dou z square. So mu comes into picture. Viscosity we need to know. So option 3 we need to know. 1 and 2 we need not know. So option B is the answer. So option E is none. So answer to this particular problem is option B. 1 and 2 only is the right answer. So that's all for today's class. Friction factor will be one of the outcomes of the solutions. Yeah, we can estimate it from the solution. Reynolds number is not needed as no scaling of governing equations needs to be done. So it is a dimensionless parameter, so it need not be known. Friction factor, rather it can be estimated from the CFD solutions. So that's all for today's session. Thank you for attending. If you have any doubts now, you can ask. I'll clarify them. So again, next class will be on next Saturday. I mean that is coming Saturday. We will solve the practice few problems that will help you for the next week assignment. That is week 2 assignments. So if you have any doubts, you can ask, or if you have any feedback to give on you want anything in any particular format, that also you can say. So yeah, thank you guys for attending today's sessions. If you have any doubts or anything needs to be clarified, we can do it now. Oh, there are some. Thank you. Yeah, thank you. Yeah, thank you. Yeah, if there are nothing to be discussed, we can close the session. We'll meet again at next Saturday, same time, 3 p.m., and we'll discuss more problems then. Thank you. And if you have any feedbacks, you can always let me know. Like these videos will be available to you, and the PPT will also be available. So if you have any suggestions, you can let me know in the next week so we can implement it. And thank you. We'll see you next week.